Plastic bending. You can see my slides here. Great.
Yes, we can.
All right, we're covering the plastoplastic method. What we're going to do first is we're going to do a review of some of the basic ideas of bending. So let's start here. Okay, remember when we're doing elastic bending, MC over I, we have a linear stress distribution, right? We know if we have like a square section or any section, we're going to first have to calculate the section properties, the I of the thing. We're going to need to find the neutral axis, which for standard bending is going to be at the CG, right? MC over I. And what that means is we're going to get a stress distribution that is linear, like what we see here. That's a straight line, which means the stress is linear. It's going from the max stress to the min stress. And if we go to the allowable, if our stress is equal to the ultimate allowable FTU, then that means we will have FTU on one end and FCU on the other end with a straight line in between. Got it? Remember all that? Okay. So we have, this is our basic formula, and we're basically focused on the extreme fibers, right? For a bending moment like this, we're focused on the extreme fibers here and here. We normally don't calculate the stress anywhere else, but we could, right? Okay. If we have this section here, we know that the I is 112 for a rectangular section, 112BH cubed, right? Plug that in down here. If we have the C is going to be that height over 2. So if we take this formula, stress equals MC over I, replace this with the allowable FTU, and then rearrange it into this form, plug in the I and the C, we find this formula that the moment allowable is 1/6 BH squared FTU. Or another way of writing the stress for a rectangular section is just 6M over BT or H squared. This is if you plug in the I and the H over 2 into this formula, it reduces to this. If you plug in FTU here and rearrange for the allowable moment, that's the allowable moment. You with me? Remember all that? Okay. So normally what do we do when we're calculating bending? We're calculating the stress, F equals MC over I, and then we write a margin of safety on that. We take the allowable FTU divided by the stress minus 1, right? That's our standard approach. 90-ish% of the analysis, bending analysis out there in industry is done that way. However, if we get a negative margin, that means it's not acceptable. Or we have to do more detailed analysis to find out if it's acceptable. If we want to evaluate plastic bending, we're going to need to evaluate it on a moment basis rather than a stress basis. You got that? So if we look, let me erase what's on this slide since it's a mess now. But if we look again at our basic equation, if we had plugged in FTU into this equation and solved for the moment, because this is using FTU, the allowable, this moment is an allowable moment. You got that? So what we could do is we could say, what is the moment we have on our part? M. The margin of safety is simply the moment allowable divided by the moment that we have applied minus 1. This will give us the exact same number as if we took the margin of safety is equal to FTU divided by the bending stress MC over I minus 1. You guys understand that? That's the first fundamental building block for what we're going to do differently when we're doing plastic bending analysis. Now, there's a reason why we need to evaluate it on a moment basis, but that reason won't really be clear until you understand the rest of what I'm going to teach you today. Are you with me? So You know how to calculate bending stresses, MC over I. You know how to evaluate them against the allowable FTU. If you're weak in either of those concepts, go back to your 3261 YouTube videos and homework and practice. Got it? Okay. Now, because we're going into plastic bending, we're going to say, okay, we're going to be taking the allowable moment and we're going to be comparing to the moment that we actually have for evaluating our bending. Now, if we use this, you'll notice this is an allowable moment, but my subscript is an E. Why do you think the subscript is an E?
Is it because it's an elastic?
Exactly. You two can put a point on your homework. It's elastic. We're talking about this stress distribution, which is what we usually assume. And because of that, instead of calling this M allowable, which we could do, I'm calling it ME. And the reason is because we're going to be learning about plastic bending allowables. And for the plastic bending allowable, we're going to use MP for full plastic bending. We're going to use MEP for elastoplastic bending. That's what we're doing today. We're going to use MC for cozones plastic bending. And whenever we see ME, we're talking about the allowable for elastic bending. Use the simple formula with a linear stress strain diagram. Are you with me? Okay. That's our first fundamental building block. This is just a review, but it's focused on a different way of evaluating elastic bending on a moment basis rather than a stress basis. Sound good? Am I repeating that too much? Okay. Next idea. If we were to apply this to a section, let's just say a rectangular section, we would construct a little table like this. We break it up into elements. We take the width and the height of each element, the Y bar to each little element, the center of each element. We'd calculate our properties from this table and then we'd evaluate our bending based on those properties. Remember that? This is all from 3261. This is the easiest section we did in 3261. Now, if we actually had a rectangle like this, you don't need to make a table. It's just 1/12 pH cubed is the I, the C is H over 2, and you just plug and chug. However, I'm showing this on a tabular basis because this is the best way to solve most of the problems, because most of our sections aren't rectangular. Most of our sections are thin sections. They are angles, they are T's, they are I-beams. And for all of these, what we're going to do is break it into elements, construct a table, and then solve. You should have learned in statics how to compute properties from a table. That should have been reinforced all through 3261 as we did bending analysis of sections using this. If you got a weak foundation, go back to the 3261 videos, watch the stuff on bending. I think it's lecture 6 and following. Okay? All right. You're going to need to be strong in bending in order to do what we're going to do now. If you are strong in bending, this is going to be a baby step forward. Great. Okay. So that's how we calculate stresses for an elastic analysis. Elastic meaning, now, let's talk about that a minute real quick. Remember, this is our stress strain curve, right? Our stress strain curve, stress versus strain, it looks like this for most of our materials. When we calculate our bending stress, MC over I, and we compare that to the allowable FTU, FTU is not in the elastic range, is it? It ain't. However, so really we're talking plastic. However, we're ignoring the plastic. What we're really doing is we're pretending that our modulus, remember our modulus is the slope of this part of the curve. Remember that? E. And what we're really saying is when we do this kind of analysis and compare to this, what we're really saying is we're going up a stress strain curve. We're ignoring the stress strain curve. What we're doing is saying, look, if this is FTU, this is really the stress strain curve we're using when we calculate MC over I and compare it to FTU. It's a gross simplification, but it's done for 90+% of the analysis. Are you with me? That means it's wrong. I remember when I was managing the group back in Long Beach, one of my analysts did something, and one of my other analysts, who was one of my sharpest guys, he writes this email, "This analysis is wrong, blah, 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 blah." I said, oh my gosh, Bill, please don't use that word wrong. There are lots of things that are wrong, but all this is a gross simplification that is not quite accurate. You say that's wrong, it puts this in the wrong light. Now, there is wrong analysis, but this one is just a really gross approximation that is completely different than wrong. You guys understand that? Now, I can see some of these arguments are going to come back on your test, right? You say, this isn't really wrong, is it, Dr. Colburn? Okay, so I'm going to be measuring you based on what I expect you to do at the appropriate level of accuracy that I'm telling you is appropriate for what we're doing. But a lot of what we're doing is wrong, but it's close enough for government work. And if that doesn't scare you, it probably should, at least when you get on the next aircraft. Okay? No, actually, it's close enough. Are you with me? So this is a gross simplification. You guys understand that? What that means is, remember, this is the strain here. The ultimate strain was out here. That means we're basically only using a fraction of thing. This can't be true, but it's actually super conservative because it misses a lot of the load carrying capability. Listen, how many guys have ever run a marathon or something like that, right? Or done bench press? How many have ever gotten tired when you run? I'm a little bit tired. I'm sweating now, right? I have a friend that every time she sweats, she stops running. I'm like, oh, actually, she doesn't sweat. So maybe that means you, right? But if you stop running when you sweat, you have not exhausted your capability. So we could have a marathon where everybody stops running every time they start to sweat. But the person that keeps running when they sweat, that person will go way beyond. This is like analyzing up to the sweating point. Even though we're going to an ultimate allowable, we're pretending the thing behaves elastically. You guys got those concepts? Okay. With that said, we're going to look at plastic bending. So we're still going to be going to the same allowable, right? FTU. We can't go higher than that. This part can't take it. But we're going to use a method that evaluates the additional capability as it starts to strain faster and faster. Okay? Okay. So let's take a look at this allowable moment. We've already kind of laid the groundwork. This is a part. You can see it's under a moment, right? We're looking at the side of this part, the cross section. You just take a section cut and pull that puppy out. We got it bending like this. You see that? Okay. And as our beam bends, it experiences this linear strain, right? If we look at the cross section, we can see if we broke this up, take our cross section, break it up into a bunch of imaginary strips. We can look at each little strip. The stress at the middle of each strip is just MC to that position over I, MC over I. So that means the stress is getting high, low, low, low. Can you imagine that? See the stress at each little point? It's going a linear distribution. We can actually look at the stress on each little strip. And if we did it this way and just calculate the stress on this little strip, the stress, the M, this distance, right, to the middle of that little strip. And then the M, the middle of that little strip. What we get is a stress here, a stress here, a stress here, and stress here, right? And you go down and then you go this way. You see that? Now, we don't need to do that because basically we can just do MC over I for our stress. But when we go to plastic, we're going to need to use this kind of approach to evaluate the stresses if we want to keep it simple. Comprende? ¿Te gusta? Nishiwanma? Okay. Blah, blah, blah. All right, we said, okay. Now, so what that means is, since the strain distribution is linear, we could take the distance to the point. So this, if we call this y from this y minus y neutral. So basically, if we say, okay, this little strip here, let me erase the stuff on the slide and redo this so it's a little clearer. This is laying the groundwork. We're actually not going to use this particular method, but it lays the groundwork for what we're doing. So what we have is we have our cross section. We've broken it up into strips. We've got a coordinate system here. You see that? So when we plug in, if we look at the strain, not only is the stress distribution linear like this, but the strain distribution is linear like that. You see that? Because of Hooke's law, right? We can calculate the stress at each little point, and we know that sigma equals EE, right? Hooke's law. So we can actually, once we know the stress, we can just divide it by the E and we get the strain. So basically our strain distribution is linear. Since the strain distribution is linear, we could say, okay, the distance from here to the middle of that little strip minus the distance from here to the neutral axis, that's this quantity, divided by the total height of this mother minus the y neutral axis, that will give us, if we multiply that quantity times the maximum strain, the strain we have up here, that will give us the strain in each little strip. So that means we can calculate the strain in this strip by just taking its position minus y neutral axis over the total height minus y neutral axis times the ultimate strain at the extreme, right? What's the ultimate strain at the extreme? Well, if you go to your stress strain curve, it's whatever that is, right? You go to wherever it breaks and you read that off the chart. Remember that from 3261? Okay. And you could do the same thing below the neutral axis down here. You could take the maximum. Now, this was the compressive strain, and this is the tension strain. We could use that max strain on that one. And it doesn't matter if this is tension or compression, right? If this is the bottom max strain, whether it's tension or compression, that we're putting in that one. If this is the top max strain, we put it in there. And this ratio, y minus y neutral axis, and if we're above, we're going to go divided by h minus y neutral axis. If we're below, we're going to do over the y minus neutral axis. That just gives us the relative position. Since we have a linear stress strain diagram, that gives us the strain at any point. You got that? Okay. To do this correctly, most correctly, we would actually calculate the strain at each little center and then look for that strain. What's the stress? And then we plot those stresses and compute the forces from those stresses. And I'm going to show you, okay? Like we see here. Blah, 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 blah. We then can turn those in. Then once we're done with that, we could take that the force, the moment is just the force on each. So once we've calculated the strain in each segment. So we've got the strain. If we have a little table, 1, 2, 3, 4, and the strain in this little piece, and we turn that into a stress, right? We look at the stress and write the stress next. And then if we say, well, that stress is on this little area, so we multiply that by the area, that gives us the force in that. So we have the force in each of these. The moment is just going to be the force times the y minus y neutral axis. If we add up all those moments, we have the total moment carrying capability. Are you with me? That is the plastic moment carrying capability. Your book goes into this in detail. Are you with me? What this means is we can follow this approach that basically says we have a moment, we calculate the strain on each and every little strip. We make a little table, 1, 2, 3. We calculate the strain, then we look up on the stress strain diagram to get the stress. Then we multiply by the area to get the force. Then we take the force and multiply by the y minus y bar. That tells us how much moment is from that strip. We sum up all the moments, and that gives us the plastic bending allowable. Are you with me? Now, you guys should all be feeling, I kind of understand what he said. Maybe you're dragging a little behind, or maybe you're right there with me. But the basic approach gives us the plastic bending allowable. This is called, I call it the iterative slice method, or Brune's iterative slice method. This is the most accurate way to do it. And other than understanding this conceptually, and that this is the most accurate allowable, you're not going to have to use this particular method. Are you with me? However, so if you're not quite gripping all the ideas, it's kind of okay at this point, as long as you understand that this is the best way to get a plastic bending allowable. The other two ways we do it are going to be two simpler ways, not as accurate, that will do the same kind of thing. So understanding the way this works here will help us with that. Still with me? Okay. Stay tuned. Let's erase this crap and get to our next slide. Okay, so let's look at this. We've got a couple ideas here. Here's our ideas. Ultimate moment. Now, what we were calling these before was allowable moment, right? We're calling them the allowable moment. We could also call it the ultimate moment. Why? Remember, we have, when we look at our stress strain curve, we have FTU and we have FTY. These are both allowables of a sort. One is the allowable for yielding and the other is allowable for breakage. True dat? Okay. This word ultimate in aerospace, remember back to 3261, in aerospace, what we do is we take the max loads that we ever see in aircraft. Actually, there's a statistical basis. We take the max loads, we multiply it by what factor of safety?
1.5.
1.5.
1.5.
Who did that first?
That was me, Matthew.
Point, Mr. McDougall. 1.5. The max loads we'll ever see. That means we almost never see them, or probably negative. Never. Then we multiply by 1.5. That means we really never see them. And then we evaluate the stresses against FTU, against the ultimate allowable. Now, doing that, because even though the methods we use are kind of approximate, that means we're really conservative, okay? So for this reason, we can call it the allowable, or we can call it the ultimate allowable or ultimate moment, which basically means it's the allowable moment, but it's the one that we're going to compare to ultimate loads, the ones that include that factor of 1.5. You with me? Okay. The next idea is this concept of the modulus of rupture. Okay, this is, I don't like the word here, but I'm going to give it to you because this is what it's called most of the time in industry. Remember, we took our stress, F equals MC over I, and we plugged in FTU for this. What we're going to do, what that means is that FTU that we use is the allowable stress. Now, if we look at our stress strain curve, that means it's this value, right? But let's say we've gone and calculated the plastic bending moment that accounts for plastic bending. If we use that value, now that's going to be bigger than the elastic moment, isn't it? It's going to be bigger. That means if we plug that moment into our formula, MC over I, it's going to give us a stress that's higher than FTU. If we look at the stress strain curve, it looks like this. This is FTU. If we plug in our plastic moment into MC over I, that's going to give us an allowable, and it's going to be higher than FTU. What it does is it's going to give us a value up here. Can the stress ever get this big? No, never. It can't go above FTU. So this stress that we calculate if we plug our plastic moment into MC over I is a fictitious stress, which basically says, remember, with our elastic analysis, the stress strain curve looks like this. And when we do elastic analysis, it's kind of like we're doing this to ME. What this does is it goes up the same thing to to F. This is based on ME, but it's actually to FTU, right? And this goes up to F modulus of rupture, which we can call FB or RB or FRB, okay? You see that? Okay, so maybe some of you are close, but you don't quite get it and you're a little confused. Let's do it one more time. Here's our stress strain curve, okay? This is the real stress strain curve to FTU. If we do an elastic analysis, we're actually doing this. This is FTU. And we're actually, because we're assuming, remember, we're assuming a linear distribution of stress like this. It's like the modulus never changes and we go straight up to FTU. That's what we're actually doing when we use our moment in the way that we do, and that's equivalent to ME, okay? If we do a plastic bending analysis, we're going to calculate either MP, which is from the Bruin iterative slice method, or MEP, which we're learning today, or MC, which is the Kozone method we learn next class. These are three different estimates of the allowable moment based on iterative slice method, based on elastoplastic, based on Kozone's method. And if we plug that into the formula, stress equals M plastic allowable C over I, that's going to give us an allowable stress that's called the modulus of rupture. And that is like as if we had gone all the way up to some new F modulus of rupture. Do you understand that idea? What it allows us to do, now we can write a margin of safety. We can say the margin of safety is just FRB over F over the calculated stress minus 1. And that approximates the plastic bending. Or we can write our margin of safety, and we're going to do this more often in this class, MP over M minus 1. These two methods are equivalent, but this is called the modulus of rupture, and it's a fictitious stress. The stress actually can't go above FTU, but it's kind of like a stress that we could use to get the same answer. Got it?
So it's just like another way of finding margin of safety. It's like over-designing a little bit, I guess.
Not over-designing, getting closer to the real number.
Okay.
With an approximate fictitious number. Got it? It's kind of like, let's say we have 3 Marvel superheroes in our class, and we're going to be fighting against the philosophy students. So let's say I have 6 students total, 3 normal students and 3 superhero students. And these guys are worth twice the other students. I really only have 6 students, but it's like I have 9 because these are worth 2. So we can say, we're calculating this based on 9 students, but there are really only 6. There can't be more than 6, but 3 of them are super. Got it?
When you put it like that. Sorry.
Yeah, baby. My daughter would like that one. Of course, she has decided she wants no part of my class. Okay. All right. Another idea is the shape factor. All right. There's 2 factors we're going to use for shape factor, and it's a little confusing. The first shape factor is if we take this ratio, if we calculate using any of the plastic bending approaches, the allowable plastic moment, which we can call MP, MEP, or MC, right? Divide by that by our allowable moment for elastic, ME. That ratio is what we call the plastic bending shape factor. Are you with me? So we can say, what's our moment? Once you calculate the moment, you can divide it by the elastic moment that you get by just plugging an FTU into MC over I. And that's like a measure. So what that means is, will this number, this K, will this be higher than 1 or lower than 1?
It's higher than 1.
It better always be higher than 1. Why?
Because we know that because I know that the FRB is only greater than FTU. So.
Right. You can put a point on your homework. MP is always going to be higher than ME. It can be equivalent or more. And therefore, this will always be bigger than 1. Some values will be like 1.1. If you have a really efficient section, like an I section, it'll be around 1.1. If you have an inefficient section, like a square section, it will be much higher, like 1.5. Got it? Okay. When we get to next lecture, we're going to learn another shape factor, the cozone shape factor. It's similar but diferente, so don't confuse the two. The other one's the cozone shape factor, and this is the plastic bending shape factor. This is just the ratio of the moments. Got it? Okay. Elastoplastic, this is the method we're going to cover today. Plastic Brunzitter slice method, that's the one I just covered. You don't have to know, you just have to understand conceptually. Cozone's method, that's what we're going to cover next time. Okay, we're ready to start the lecture. But actually, we spent so much time in the fundamentals, you should be ready to just absorb this quickly. And then you can go back to the YouTube video if you need to review on any piece of this. Okay, so let's take a look at this one more time. This is our actual stress strain curve. What we're going to do when we do an elastoplastic analysis, remember we said that if we do an elastic analysis, we're kind of like we're actually doing this, didn't we? Isn't that what we said? With the real thing, it's doing this. And if you use the method I covered for plastic, it would account for this whole thing. This gives us MP. This gives us ME. And if we say, no, let's forget this is too complicated. Let's just pretend we go from 0 to FTU and it's constant until the ultimate strain. This is FTU, right? And it's constant rather than this. This will give us the elastoplastic analysis, the moment. Okay? Got it? You understand that concept? This is not yet how we're going to do it, but this is understanding of what it's really doing. Okay. So here's how it works. Here's a section. We have a moment applied. If we do an elastic analysis, we're going to get a strain distribution like this. And our stress distribution is also like this. True? This is for M sub E. If we do that plastic analysis that I covered at the beginning where we look up the strain at each point, we would get this curve. And this gives us what's called MP. We're not learning how to do this. We just need to understand it conceptually. If we use the elastoplastic method, that's what we're focused on now. What we're going to do, remember, we can't get above FTU and FCU, right? We're just going to pretend if this is the neutral axis, we're going to pretend everything above the neutral axis is at FCU. Everything below the neutral axis is at FTU. See how easy that is? Remember before, what we had to do was look at how much stress is on this little slice and how much stress is on this little slice and how much stress is on this little slice. Right? We got this little thing. We get this stress, a bunch of stresses. We have to look at each one and where they're located. With this method, all we got to do is say, oh, here's the neutral axis. That's all in compression, FCU. This is all in tension, FTU. Look how easy that is. There's one little trick that will bite some of you, so pay attention. But this is going to be really easy. You with me? Okay. Let's erase this crap. All right. Here's our section. If we're fully elastoplastic, this is what we said, right? Everything above is at F. Now, let's say we have a symmetric stress strain curve. That means it's the same in compression as tension, right? What is FCU?
Same as FCU.
It's just FTU, because if it's symmetric, that means it's the same for tension and compression. So in tension and compression, we're both using the same magnitude FTU. That means everything above is at FTU, everything below is at FTU. You got it? This is a little bit of a tangent, but it's critical. Here's the deal. If you have a part and all you do is you look in your handbook, you find FTU for the part, you're going to assume this is all at FTU and this is all at FTU. This is just negative FTU and that's positive FTU. True, Dad? But, big but, you can use one T or two T's. Don't be a but. Pay attention to the but. Okay, I know. If I give you a full range stress strain curve, then what you're going to do is read FCU from this, FTU from that. Everything up here is at this value, everything down here is at that value, right? If the moment's going like this, that means compression on the top. This is at FCU, and this is at FTU. If the moment is going like that, you'll put all this at FTU and all this down here at FCU. You got it? How many guys go, yeah, I got that? Okay. I'm moving really fast now, but you should understand that. Okay. With that said, we can say, okay, for this method, all we're going to do, oops, I didn't mean to do that. We're going to say, okay, we had a moment like this. Therefore, all this is in compression at FCU. All this is at tension at FTU. If we take that stress, now look up here. That means this is all at which one? Let's say our FTU is 100 KSI. What is the stress on this part?
100 KSI.
Minus 100, yes. What's the stress on this part?
100 KSI.
Plus 100, yes. What is the force if all of this up here is at minus 100? What is the force on this part? It's just FCU, which is 100, times the width, B, times H over 2, right? That's the force on that piece. It's a negative force, right? What's the force on this piece? It's the same value. It's positive. Where are they centered? Well, if this is H for this section, that means H over 4 h over 4. How much moment does this force cause about the neutral axis? It causes this force, which is FCU times B times h over 2 times h over 4. That's the moment on this piece. And this one, and that's a negative. Actually, that force is compressive, but it's up above. That's going to give us a positive moment, right? Down here, we've got the same force, the same distance. That's also going to give us a positive, because that's positive at a negative value, and this is negative at a positive value. So that ends up those two moments add together. If we sum those two moments together, this plus this, that gives us the total elastoplastic analysis. Woo! Now that might seem like magic, so let's do it systematically with a table. Okay. Stay tuned. Erase this crap. Bang. And let's get to the next blah, blah, blah. We said this, right? Here's the moment is the force times h over force times h over. This is once we have taken the force is just FTU times B times h over 2, right? Okay. So here's how we, here's comparing our methods. Elastic bending gives us a linear distribution and it calculates the moment like this, and that's our elastic moment. Elastoplastic bending uses a distribution like this, and this is our allowable moment. This allowable moment here is only valid for what kind of sections?
Rectangular.
Rectangular. Don't go using this elsewhere. We're going to calculate it the way I'm going to tell you. But if it's rectangular, it's going to be the same thing. Now, what's our plastic bending shape factor? We take our MEP, we divide it by our ME, and we get that factor. Got that? Now, if we plug in all our values, we're going to find what is the plastic shape factor every time we have a rectangular section.
1.5.
1.5.
1.5. Is it 1.5 for any cross section?
No, only
Nope.
for
No,
rectangles.
because we plugged in the I and the C for a rectangular section. This is only true for a rectangular section. So if I give you a rectangular section and I tell you what the elastic moment is, what do you need to do to calculate the plastic moment? Well, if you can go through the whole process and take 15 minutes, or you can just multiply by 1.5. But if it ain't rectangular, don't multiply by 1.5. Comprende? Okay.
Professor, can you repeat that? What are you, so I get that it's always 1.5 because of the way the equations break down. What are you multiplying by 1.5 to get what?
Oh, if I gave you, if I said, hey, what is the plastic, if I gave you the, if I said, hey, the elastic allowable is this, or if I just give you the moment, right, the stress, I say, if you take FTU and you plug into this MC over I, then, and you solve for the moment, that's going to give you ME. If you take that ME and you multiply by 1.5, that gives you that elastoplastic moment. If it's a rectangular section. If it's not rectangular, you'd have to calculate ME for the section, then you'd calculate your MEP for the section, and then you'd calculate your ratio to find out what factor you have. Does that make sense, Gerald?
Yeah, you're just taking the moment out of that equation and then, which is ME multiplied by 1.5 to get MEP.
Right.
Okay.
Okay. Blah, 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 blah. Okay. Here we go. Let's just take a look. Let's solve this on a rectangular section. Now, what I just did was just using, hey, if it's rectangular, we can just do 1/12 BT cubed, right? Or BH cubed, and plug in C is just H over 2. Or we can actually solve it using the systematic section. Here's how you do it. You'll break your section up into rectangles. So if I have a rectangle, if this is my cross section, what we're going to do is first we're going to break it into pieces. And what we need to do is break it up at the neutral axis. We're going to assume the neutral axis is at the center. Are you still with me? That means if we have a rectangle, we're going to break it at the neutral axis. This we'll call this element 1. We'll call this element 2. And then we're going to construct a table. Are you with me? It's just like we did analysis before, only now we're going to do it for plastic bending. We identify our coordinate axes, right? We break it up into segments. We said that. And then we're going to construct our little table. There's a detailed procedure here. Blah, 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 blah. Okay. We're going to see how this plays out in a minute. But basically what that means is we're going to draw our section, define our coordinate axes, find the centroid, call this element 1, call this element 2, okay? Then we're going to construct a table, and we're going to calculate our elastic plastic moment, and this tells you how we're going to do that. And then we're going to evaluate the forces, and we're going to find out when they sum to 0, okay? Let me explain this on the next slide in more detail. When you're actually doing this, you'll find this step-by-step procedure in your handbook will be helpful. But let's first understand how it works on this section, which we're going to do right here. Here's a rectangular section, and we're going to solve the method. So what we're going to do is we're going to say we're going to construct our table. We're going to put the width and the height in for each element, right? So we construct our table. This is a what? It's a 1 inch. It's a 1 inch by a 1 inch by 2 inch piece. 1 inch. Yeah, 1 inch by 1 inch piece. This is a 1 by 1 piece. All right. So that means we're going to break it up, but we're going to pretend the CG is there. The width is 1 inch. We put that in here for the width. The height of that is going to be 1/2 inch, right? And the Y bar of that from our thing here is going to be h/4. True that? And then we're going to do it again. This other one is the same width and also 0.5 tall. And, I'm sorry. This upper one is the first one up here. So that means the distance to centroid here is 0.75, right? From here to here, 0.75. And the one from here to here, that's 0.25. Got that? We're going to plug in our E. Actually, you're not going to need this for most of what we're going to do. Then what you're going to do is you can say, okay, what is the area? Well, it's just this times this, okay? And what's the AY bar? Great, okay. Then what you're going to do is you're going to say, all right, what do we do with the top of this? Oh, what this is doing is this is going through the process to calculate. This is what we did in 3261 to calculate the elastic moment. We calculate our properties, and then we just plug into this formula, right? The elastic moment, we're calling that ME. This is old nomenclature, is equal to FTU times I/C. Once we've calculated I divided by C, which in this case is the Y bar, that gives us ME. True that? This is what kind of analysis? Elastic analysis from 3261. Okay, all right. Now we're ready to do plastic analysis. To do plastic analysis, there's two ways we could do this. Since it's a rectangular, we could just multiply by 1.5. That's really fast. Or what we can do is say, okay, all of this is under compression. That means it's 75 KSI. FTU, 75 negative KSI plus 75 KSI. True dat? You just take this area, this stress, times this area, and what does that give you? That gives you P. So 75 times 0.5, what's that, 30 blah, 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 blah. And we get the force. We now sum our forces. Is this force here positive or negative? If we multiply negative 75K times this area. The negative force, right? Is this force, this times this, positive or negative? It's positive. When we sum these up, these sum to 0. If this piece has a moment on it, how much axial load is on the part? 0, right? The upper part is in compression, the lower part is in tension, but there's no axial load. So this has to sum to 0 when we add these two pieces together, okay? Now, if it sums to 0, we're ready to calculate the moment, which means we make another column and we just take this force times the Y minus Y bar of this section. And that's the moment that this first strip causes about the neutral axis. And then we take this force times its Y minus Y bar, and that's the moment that one causes. If we sum those, and we got to be careful with the sign, right? This was a negative stress, this is a positive, or a negative force, positive force. So that means using right-hand rule, Y minus Y bar times this plus Y minus Y bar times the other gives us the total moment, and that is our MEP. So since this is rectangular, we can just multiply this by 1.5, or we can apply a plastic bending analysis, okay? Let me clean this up and we're gonna see that done here, okay? This was using our elastoplastic method. So here's where, with the plastic bending analysis, you'll see we calculate. Now, what I didn't do here is what I should have done is inserted FTU here. It really will help you if you put in a column that has the allowable stress. The upper piece was at what stress? If we have a moment like this, a positive moment, the upper one is on FCU, so it's negative FTU. And the lower one's at FTU. So it's negative on the upper one, positive on the lower one. Then you multiply that value times your area, and that gives you your force. You got that? This value times your area, that gives your force. Do these two forces sum to 0? Let me clean it up a second. Do these two sum to 0? What's 37.5 minus 37.5?
0.
0.
0. That means we found the neutral axis. If this was non-zero, we're going to have to change it. Okay? And if you look through the procedure, I tell you exactly how to do that if needed. If this does sum to 0, then you take this, right? That's the force, times y minus y bar, and that gives you the moment. And then you do this times y minus y bar, and that gives you this. Now this ends up being positive times positive. This ends up being negative times a negative quantity. So they both end up being positive moments. You add them together, and that's the total moment carrying capability. This is MEP. You'll notice this is identical to this that we got just by multiplying by 1.5. Why? Because this is rectangular. If it's rectangular, you can just multiply by 1.5. If it's not rectangular, you're going to have to do this process. Are you with me? Now, this one actually summed to 0, but it often doesn't, okay? If we had, let's say that we have a section that's not symmetric. If it looked like, let's say our part looks like this, or actually, let's say that our FTU is 75 KSI, and our FCU is 100 KSI. Then when we multiply this out, these would be different forces, right? When we sum this up, we end up with a value. It's not 0. Then we're going to use the equation in our handbook that calculates delta H. And that delta H will tell us, we thought the neutral axis was here. Now we have to move it either up or down using this delta H formula. We'll have to construct a new table. Now our new section, once we've moved it, we'll have a new neutral axis. You notice this one was in the middle. This is at a different location after we applied this delta H. And we do the same process again. And if that sums to 0, then we're going to find the answer, okay? We're going to see another example here in a moment. Let's do that on the next slide. Okay, so here's an I section. And here is, so if we have an I section like this, now this one we can't just multiply by our factor. What we're going to do is first break it into sections. Look, I broke it into 4 sections. You see that? 1, 2, 3, 4. Now, if we were doing elastic analysis, we would have to have more columns in our table and calculate the I of the section like we did in 3261. And if we're doing both elastic and plastic analysis and comparing them, we will have to do that as well. If we only want the plastic bending and allowable, all we need is these entries in the table, right? All we need is we put in the width of each element here, right? The first one is 2 inches. The second one is 0.1 inches. The third one is 0.1 inches. The fourth is 2 inches, right? Then we put in the vertical dimension of it, which is, this is 0.2. This one was 1.3. This one's 1.3. This is 0.2. You got that? Then you put in the Y. That's the distance from here to the middle of there. That's 2.9. From here to the middle of there. That's 2.15. From here to the middle of there. That's this one. Here to the middle of there. That's this one. Then we multiply this times this. That's the area. This times this. That's the area, right? We put in our allowable. Everything above the neutral axis is in compression, the compressive allowable. Everything below the neutral axis is the tension allowable. You'll notice our tension and compression allowables are different in this case. We sum this up. Do these sum to 0? These don't sum to 0. That means we would have to do it again, right? We're going to have to calculate delta H. So you can ignore this column because this is wrong, because this summation is not 0. Got that? Once we have this, we now say, okay, let's take this little value, right? If we sum this up, minus 58, plus 78, plus 78, we get a value. We plug that in here. Got that? Then we take FTU, F of the upper. What was the FTU of the upper? The F allowable of the upper was negative 58 KSI. So we put in negative 58,000 minus this one, which is plus 78,000, right? All that is times T. Well, what T? Actually, you look at your neutral axis. The neutral axis was assumed here. What is the horizontal width of the thing at the neutral axis? That's the value put in there. You got it? It's not necessarily T of the part. It's whatever that horizontal width is at the neutral axis. True that? Okay. And then we calculate this quantity. And what that does is give us a value. If we plug in those values, let me erase this slide real quick. If we plug in those values, you'll notice we got a negative number. That means we thought the neutral axis was here. Because this was non-zero, we know that ain't the right value. This tells us we need to move it up or down. Down.
Down.
That means we're going to say, okay, it was at 1.5. 1.5 minus this value gives us the new neutral axis. We're going to have to do this problem again. What we're going to have to do now, you'll notice these two parts are unchanged, but you'll notice now this one got longer and this one got shorter. So we're going to need to construct a new table. You understand that? Let's see how that works. Okay, I'm going to erase this crap and we will continue. We calculate our new neutral axis, which was the old neutral axis minus this delta H. And then we adjust these two elements to account for that. You see how, since it moved down, this one got smaller, that one got bigger. Now we need a new table. You'll notice this is the same, this is the same, this is the same, this is the same. These are all widths. This is the same, this is the same. You'll notice these two values change, the height of them. And the Y bar of those two elements changed. That means the area of these two elements changed. Everything above is still negative 58. Everything below is still plus 78. We multiply that stress times this area, this stress times this area, and so on. And we calculate this. When we sum up all these forces, what do we get down here?
0.
0. Have we found the neutral axis, the true neutral axis? Yes. Since it's, now if it didn't sum to 0, we'd have to do it again. But if you use this section, if you use this formula, and if the thickness doesn't change, the width of the part doesn't change between the old and the new, if the width of the part doesn't change between the old and the new, then this will nail it. This process will nail it in 2 iterations. If the width changes from the old to the new, you will have to do another iteration and maybe more. But if the width doesn't change, 2 will nail it. Okay. How do you know if you nail it? Because your sum of the forces is 0. If your force is summed to 0, you now have found the centroid, and now you can calculate this. We shouldn't have calculated. Oh, look, we didn't calculate the moment here. But we are going to here because now this sums to 0. So now we take this force times the Y minus Y bar that we assumed, which is at this value, not the old CG, but this value. I'm sorry, not this. Yeah, this value. This is the distance from here to here. That's the Y bar, right? Y minus Y bar. Y minus Y bar. And we calculate the force, or excuse me, moment. Add those mothers together. This is MEP. Got it? That's the process. Let me warn you about something here. This is our basic process and how you're going to apply it. With this one, in this first one, you'll notice when we applied the process, was the thickness the same from our first iteration through here to our second iteration through there? Has the thickness or the width between here and here changed?
No.
No. Therefore, how many iterations of elastoplastic, how many tables do we need?
2.
2 max, right? Now, if our stress on the upper and lower, if this is symmetric and our stress on the upper and lower is the same, just positive and negative, we will converge in 1 table. If our stresses are different, we will converge in 2 tables if the width hasn't changed. But if, let's say we go from this first neutral axis to this new second neutral axis, has the width through this section changed? Yes.
Yes.
That means you're going to do 1 table and you find out delta H. You're going to do another table and then you're going to get another non-zero P, which means you're going to have to do delta H again and another table. Now, if the next one gives you a delta H that stays in the same thickness, you'll be done after that. But if you drop back down into here, you're going to have to do it again. You see that? If the delta H changes thickness between the 2 iterations, you're going to have to do another table. Most of the stuff I give you is not going to have that problem, but it could. Got that?
So, Professor, so as long as you get the sum of PI 0, that's good.
Right. If you sum of forces, if you do the thing correctly, and the sum of forces 0, you know you found the proper one. Now you calculate the moment, and that's the MEP. Okay. All right. Let's look at another case. What if you have a crap like this? Now, I can't think of any place I give you one like this. Will delta H ever be in the same width part? Not ever. What does this mean? That means you're going to have to make a bunch of tables. How many? Probably 3 or 4, and you'll get close enough for government work. What you'll see is you'll see P getting smaller and smaller and smaller. It won't quite be 0 unless you get, now if you do this in Excel, you can nail it. Right? You can do a goal seek. But by hand, you're going to have to do a few ones. Eventually, your P will get relatively small. You say, close enough. Calculate your moment, done. How many times you do it? As many times as you can. If you're on a test, do it maybe 3-4 times and then go on to the problems, leave some room for work. Because if you get done with the rest of the test, you can go back and do a couple more and make sure you nailed it. But a close answer is better than no answer, right? Comprende? Okay. All right. So this is really straightforward. This one's a little harder. And the third one, you just got to iterate a couple times more. Okay. This is what we end up what was I going to talk about here? Oh, I was going to tell you what happens. Remember all of these, if we have only a moment, no axial load. What happens if we have a part that has moment and axial load? I mean, a force and an axial load. Excuse me, a moment and an axial load. If that happens, then actually you sum this up to your P rather than to 0, whatever that force is, whether it's tension or compression. And that's the way you would do this for one that has a force also. I can't think of one problem I gave you that's like this, and I'm not planning to. This is just alerting you. So if you get out there in industry and you have one that has axial load also, this is how you would do it. Okay. I don't yet have a video that goes into this. When I put one together, I'll probably put it in my playlist that's almost identical to yours, but it's for industry professionals. But for now, all you need to do is be kind of alert that if you get a P, you would sum this up to that force, not to 0, and that would be how you find your neutral axis. Okay. You guys understand that? Okay. This is how we can write margins of safety, right? We can take the F modulus of rupture divided by the stress, or we can just take MEP. Mostly we're going to use MEP over M minus 1. If we want to determine the maximum elastoplastic moment, what is the best idealization to use? This is an important question. This A, B, C, or D? Anybody
C.
say A?
C.
D and D.
Who says A? Anybody? Does anybody say B? Does anybody say C? Why do you say C?
Because,
Put up the neutral
we
axis.
have
Like
like
the
cut off in
axis.
the upper and the lower.
Breaks to the neutral axis. How about D?
Also D works.
Also fine. Either of those will work. You have to break it up at the neutral axis. And then if we do another iteration, we will have to break it at the new neutral axis. That's how we do it. Got it? Enjoy.
Thank you,
Grazie.
Professor.
Thank you.
Thank you,
Thank
Professor.
you.